In this lecture, I'm going to continue my previous lecture on DC Machines 2 presentation. Before I continue, I will just remind you what we have so far discussed. We were talking about classification of DC machines. Um, Basically, there are two types of excitations used in DC machines. One is electromagnetic excitation. The other one is permanent magnet excitation. So we first talk about electromagnetic excitation, and there we said that this is actually the magnetic field required for the machine is generated by externally supplied electricity, right? A DC source. So that uh, that is called the field. So that field can be supplied externally by a separate DC source. Then it is called separately excited DC machines. Or it can be supplied, the field current can be supplied as a part of the armature current, or maybe the whole armature current will also be used to supply the field coils. That is called self-excited DC machines. Then this is called the separately excited DC machine. One supply is connected here and the other supply is connected to the armature. And then we talk about the self-excited DC machine, where both the armature coil and both the armature coil and the field coil are supplied by the single supply in series. So in that case we call series self-excited DC machine. And the other type is called the shunt excited DC machine, where the armature coil and the field coils are in parallel to the same supply. Then it is called shunt self-excited DC machine. And then we say that there are some certain advantages and disadvantages of series and shunt connections. So by combining those two, we can make a type called compound self-excited DC machine, where we have one field coil in series with the armature coil and the other one in parallel with the armature coil. So again, these compound self-excited DC machines can be classified into two separate kinds. One is called cumulative compound and the other one is called differential compound. So when we say cumulative compound, the fields generated by when we say cumulative compound, the series field is connected to aid the shunt field. That means the two fields generated by these coils are summative. That means they are jointly they are getting added and make this signal field strength stronger. And the differential compound means the two fields are opposing each other. Then the total resultant magnetic field will be reduced. So we discuss about the different characteristics of these connections, and then we said that these compound machines, the field coil connection can be again we can connect the field coil in two different ways. I mean, the shunt coil can be connected into the machine in two different ways. One is called short shunt, where the field coil, the shunt field coil is parallel only with the armature, and the long shunt, the shunt coil is parallel to both the series coil and the armature coil. Then it is called the long shunt. And then finally we talk about the permanent magnet excitation, where instead of making the magnetic field using external DC source, we can use a permanent magnet to provide the required magnetic field for the machine. So then they are called permanent magnet excitation, and it is classified as a separately excited because the field strength is independent from the armature current, right? So the excitation is independent from the armature current. So and we said that this is normally used for smaller machines, um, because to make bigger machines it is expensive to make powerful magnets, and also the size of the machine will be larger because of the size of the magnet. So we can produce the magnetic field electrically, what we call the uh, electromagnetic coils, to have higher field strength, and also then the field strength can be controlled by controlling the supply to the field coils. Therefore these machines are not very much used in the industry, but we use it for smaller uh, the machines like what you find in toys, small motors, right? So that is where we stopped last time, so I will start from that point onward. uh, Characteristics of DC machine, and we start with generators. I hope you remember now, DC, when we talk about DC machines, the construction of generator and motor are same, almost same. Therefore uh, but when the way that we use it makes it the generator or the motor. So now we are going to talk about generators. The generator characteristics. Um, the speed of generator is mainly uh, dependent on the prime mover. That means if it is a generator, we have to rotate it now using some external power, mechanical power. Maybe it is um, uh, hydropower or thermal power, whatever it is, right? So speed of the generator is mainly controlled by the external mover, prime mover, right? uh, and that speed is normally having speed governors to maintain a constant speed. So so therefore for DC generators we have to make sure that um, the driving power will drive the generator at a constant speed. Otherwise the generated voltages will be changing. And then the performance of the generator when the speed is constant deals primarily with the relationship between excitation, terminal voltage, and external load. So I mean the performance mean the output of the generator will depend on the excitation, the field excitation, and the terminal voltage that we require, and also the external load. If you are connecting some circuit or whatever appliances at the end of the terminals of the generator, will decide on the performance of the machine. So so these relations are best described by means of curves known as generator characteristic curves. So mainly there are three types of characteristic curves. One is open circuit characteristic, second internal or total characteristics, third external characteristics. So these are the three types of curves that we are going to talk about. which will explain the characteristics of a generator. So if we first look at open circuit characteristics, it is called OCC, open circuit characteristics. That is mainly the generated EMF E0 against the field current, right? The current supplied to the field. So so this is the relationship. When you increase the field current, initially, even though the field current is 0, if the machine is generator is rotating, it will generate a small voltage, and then when you increase the current, the generated voltage, output voltage will go up, and after one point the output voltage becomes almost constant even though you increase the field current. So and this is, remember, open circuit characteristics. That means no load is connected between the terminals of the generator. So IF, you have increasing while keeping the rotating speed constant. So so this curve sometimes called magnetization characteristic, so no load saturation curve. So here if we look at the special areas here, the shape of this curve is common for all generators, whether separately excited or self-excited. This curve will be same, and you notice that there, when there is no field current, small EMF is generated. That is due to residual flux. That means even though current is not supplied, there will be very weak magnetic field, which is called the residual flux. Due to that, it will generate a small amount of voltage here. And now if the field current is increased, the flux increases linearly initially, and after that the curve becomes a straight line, flat line, and this is called saturation. This is the linear region. So however, when saturation begins, the flux becomes constant. So this is due to constant flux, because when we learn about magnetism, we found that even though you increase the current, you can't increase the magnetic flux further. It's called the saturation. Yes, like in the BH curve, BH loop, right? So the same thing happens here. And then this characteristic can be obtained experimentally by operating the generator at no load and constant speed, and recording the change in terminal voltage as the field current is varied, right? So by varying the field current, you can measure the output voltage and draw this type of curve. So this open circuit characteristic curve is known at a certain speed n1. If you know this curve for a particular speed n1, the OCC at another speed n2 can be easily predicted. This is because for a constant field current, the ratio of the generated voltage is equal to the ratio of the corresponding speeds. So that means when the field current is constant, the generated EMF is totally dependent on the speed of the uh, rotation of the generator, right, at no load. So therefore E01 over E02, E01 we have proved that it is K phi N1. K is called the armature constant, phi is the flux, and N1 is the angular velocity, rotation speed. So this divided by this, so these two are equal because the field current is constant, so the ratio becomes N1 over N2. So that means E02, the generated EMF voltage, can be found if you know the generated voltage at a certain speed, and then you can find the new generator voltage for a new speed. So this type of simple equations you have to remember. And then that is the first kind of characteristic curve. The next one is called the internal or total characteristics. So that is E versus IA. IA is the armature current. This curve shows the relationship between the generated EMF on load. Now previous it is called no load, that is why we mentioned it as E0. But now we are going to consider with load, right? That means you have connected some load to the terminals of the armature coil terminals. Then this EMF generated by the armature and the armature current IA. So this is called the internal or total characteristics. The previous one, which was called OCC, that is open circuit characteristic, was drawn between the generated EMF against field current, right? But this one is armature current here we are using, and the generated EMF at load, on load, right? So the EMF E is less than E0, definitely, due to the demagnetizing effect of the armature reaction. So when armature is carrying current, it will generate another magnetic field which is opposing the magnetic field generated by the field poles. Therefore total resultant flux reduces. Due to that, the generated EMF will be reduced. Therefore this curve will lie below the OCC characteristics. The internal characteristics cannot be obtained directly by experiment. We can't measure it experimentally, mainly because because a voltmeter cannot read the EMF generated on the load due to the voltage drop in the armature resistance. You know, the generated voltage will cause some current to flow. Then I try to draw it and show you that. Say for example, the armature coil, which we normally illustrate like, say this is the armature. So you have brushes in these two ends, and then the wire is going like this, and then you have the internal resistance of the armature, right? And then only it goes out like this. So like this. So the voltage generated by the armature at certain load means this voltage. This is the voltage E, right? You can measure this voltage, but this is when there is a current that is on load, no? So if there is a current I flowing on this one, IA say, then there will be a voltage drop happening here. Therefore, uh, even though you can measure this one, you can't measure this. Therefore, exact E you can't practically measure. Therefore, this cannot be obtained practically. This is because a voltmeter cannot read the EMF generated on the load due to the voltage drop in the armature resistance. So that is called the internal or total characteristics. Then the third type of curve is called the external characteristics. External characteristic means from the terminals outward. So voltage against the armature current. This curve shows the relation between the terminal voltage and the load current IA. So it can be obtained by simultaneously recording the terminal voltage and load current of a loaded generator. This is again, remember, not open circuit, this is a loaded generator. So the terminal voltage V will be less than E because of the internal resistance of the armature. Therefore, this curve will lie below the internal characteristics. So if you know the internal characteristics, internal voltage, this voltage will be less than that due to the armature current, right? This characteristic is very important in determining the suitability of a generator for a given application, right? So those are the three characteristics that we must know, and then let's look at these characteristics for different types of generators. First, let's consider the separately excited DC generator. Separately excited DC generator means the field coil is supplied with a separate source and the armature coil is supplied with a separate source. So therefore the field current is independent of the armature terminal voltage. Therefore the field current is independent of the armature terminal voltage. Separately excited DC generators, their armature terminal voltage is independent from the field current because they are separated, and the generator is driven by a prime mover at a constant speed. So the no load and load characteristics is shown here in the next slide. So the load characteristics, this is the no load curve. It's same as what we have seen before, and this is called the rated voltage E0 at no load. But when a load is connected, you will see that when the armature current goes up, the generated voltage decreases, right? So the load characteristic describes how the terminal voltage of armature of the generator changes when the armature current IA is varied. So at rated current for a generator, there is a rated voltage and rated current. So when it is operated at the rated current, rated load, you see that the terminal voltage drops a little bit from the no load voltage. So at the rated speed, rated voltage is generated across the armature terminals with no load. that means when the switch S is open, this is a special arrangement we can use to draw that characteristic curve. So when the switch is S is open, this is running on no load, right? So you can change the field coil current by changing this one, and then the motor is rotating and generating voltage. To test the uh, load condition, you can close the switch, and then there will be current flowing through the load. So for IA equals 0, IA is the armature current here, equals 0. The voltage generated here will be E naught. When S is closed, that means when the load is connected, the load current IA is increased. The terminal voltage is expected to decrease due to various drops such as armature resistance and brush voltage drop, etc. So when there is a current, due to armature resistance some voltage will drop, and also at the brushes there will be certain resistance added, so IR drops will be there in those places, so this voltage will be reduced. But this voltage drop is very small, so therefore the generator approximates to the constant voltage supply. So in the previous graph, this is a small voltage change, so we can assume, approximate, it is supplying a constant voltage. Then if we look at the series self-excited DC generators, there the output voltage increases as the load starts drawing more current. So in the series wound DC generators, if the current is going up, then the output voltage will also go up. So under low load current conditions, the current that flows in the load and through the generator is small. So at low load conditions, a small magnetic field is set up by the field poles. So because the current is small, only a small voltage is induced in the armature. If the resistance of the load decreases, the load current increases, right? So under this condition, that means if you increase the load, under this condition more current flows through the field. So this increases the magnetic field and increases the output voltage, right? So that means when the current is going up, the generated voltage will also go up, because field current is going up. So the condition is completely different from the separately excited DC generators. A series wound DC generator has the characteristics that the output voltage varies with load current. So so output voltage depends on the load current for series self-excited DC generators. So this is undesirable for most applications, right? We expect a constant voltage. For this reason, this type of generators are rarely used in everyday practice. So this is series self-excited DC generator. Now if we talk about the shunt self-excited DC generator, the current in the field winding of a shunt wound generator is independent of the load current, because they are two different parts. uh, sees the field current, and therefore the field strength is not affected by the load current. The output voltage remains more nearly constant than in the case of the series wound generator. Therefore, the output voltage of a shunt generator varies inversely with the load current. So that means when the load current goes up, the voltage goes down, not like in the case of series self-excited DC generators. The output voltage decreases as the load current increases, because the voltage drop across the armature resistance increases. That drop is actually due to the armature resistance. Then IR loss will go up when I is increasing, therefore the terminal voltage will decrease. So then you see the difference between series self-excited DC generator and shunt self-excited DC generators. In series one, you saw that when the load is going up, voltage increases. In shunt one, you saw that when the load is going up, generated voltage will go down. So in the case of a compound self-excited DC generator, these two things will combine together, right? So in the compound, that where you have both series field winding and shunt field winding, right? So if the compound generator, when the load increases, the armature voltage decreases just as in the shunt generator, right? So when load is going up, for the case of a shunt generator, the voltage decreases, armature voltage decreases when the load goes up. This causes the voltage applied to the shunt field winding to decrease. So shunt field is connected across the armature terminals, therefore the shunt winding, the field winding is getting a lower voltage. So so it will decrease the magnetic field, right? So this same increases in load current, the same increase in load current, since it flows through the series winding. Since it flows through the series winding, because here we are talking about the increase of load now. So when the load goes up, the armature voltage decreases because of the armature resistance, right? But when voltage decreases, the field coil is getting a lower voltage, so it will reduce the magnetic field, and the same increase in load current, since it flows through the series winding, causes an increase in the magnetic field produced by that winding. So shunt winding, when the load is going up, shunt winding field reduces, series winding field increases, right? Therefore by proportioning the two field, so that the decrease in the shunt field is just compensated by the increase in the series field, the output voltage remains constant. So that is depicted by these two graphs here. This is the series wound DC generator. When the load goes up, the voltage goes up. For the shunt wound DC generator, when the load goes up, voltage decreases. So when you have both, you can keep the the output voltage constant, even though the load is changing. So that is the advantage of having compound self-excited DC generators. So if we now come back to series self-excited DC motor, the speed is restricted to 5000 revolutions per minute. The motor must not be running with no load, as this will cause the motor to accelerate uncontrollably. So series DC motors can develop 500 to 800% of full load torque upon starting. So at the start, the DC motors can develop 500% to 800% of full load torque upon starting. So it has a very high torque at the starting. The series motors are suitable for applications requiring a high starting torque. For example, like cranes, hoists, gates, power tools, and automobile starters. They need initially very high power. For example, if it is a crane, initially to lift the weight, you need very high torque. When it is moving, you need a smaller torque. So for such applications, you can use this series self-excited DC motors. Right. So however, series DC motors are not suitable for loads requiring torque to increase with increasing speed, such as fans and blowers. There are certain applications where you need higher torques at higher speeds. So for example, if you take fan, when the speed is high, the torque also must be high because of the wind resistance. So for such applications, we can't use DC motors. Our series DC motors have very poor speed control, running slowly with heavy loads and quickly with light loads. Series DC motor would never drive machines with a belt. So you can't use series DC motors that will run a machine with a belt. If the belt is broken, then what would happen? The load would be removed and cause the motor to accelerate and destroy itself in the matter of seconds. So common uses of series DC motors include crane hoists, where large heavy load will be raised and lowered, bridge and trolley drivers on large overhead loads, and traction motors used to drive trains are series motors that provide the required torque and horsepower to get massive amounts of weights moving. So initial torque is very high in series DC motors. So that was depicted in this graph, where this axis is torque. If I try to enlarge it, this graph is torque and this graph is motor speed, and you see when the motor is running initially starting, the torque is very high, but when uh, when torque is becoming higher and higher, the speed reduces. When the load is high, the speed reduces. So at no load, it is running at very high speed. right? So that is the series self-excited DC motor. And then we come to the shunt uh, self-excited DC motor. Sorry, this one. Um, there you will see the graph is different. Here it can maintain a constant, almost constant speed with varying torques, right? So therefore the shunt DC motors have moderate starting torque, is lower than the series DC motors of about 250% to 300% of the full load torque as the motor speeds up. So initially it has about 250% or 300% higher than the full load. Full load one is somewhere here, right? So however, shunt DC motor has a very flat speed torque characteristics. This like almost flat side. Therefore it can maintain the same torque as the load increases. So in other words, a shunt DC motor can deliver steady torque at normal operating speeds. Shunt motor provides starting torque that varies with the load applied. And good speed regulation by controlling the shunt field voltage. So if we can change the shunt field voltage, you can control the speed. Some common users of the shunt motors are machine shop lathes, lathe machines. You might have seen them, and industry process lines where speed and tension control are critical. And then finally we come to the compound self-excited DC motors. Compound DC motor has the field connected in both series and shunt with the armature. So this arrangement gives the compound motor a high torque of a series DC motor and the constant speed of a shunt motor. So both the good characteristics of series and shunt one is combined here. Since the flux in a cumulative compounded motor adds together, the motor has a stronger starting torque. And common uses of compound motors include elevators, air compressors, conveyors, and pressers are using these compound motors. Compound motors can be operated as shunt motors by disconnecting the series field. If you just disconnect the series field, you can use it as a shunt motor. So many manufacturing process lines are designed this way. That means you can change a compound motor to a shunt motor. The reason being that most off-shelf motors are compound motors. What is available in the market are compound motors, and series field can always be connected later to provide additional torque if needed. And then finally the permanent magnet DC motors that we didn't talk about, how the torque is changing with the speed. For permanent magnet DC motors, PMDC, can develop about 600 to 700% of full load torque upon starting. At the start the torque is larger, but when the torque will reduce when the speed reduces. So have a good starting torque that falls off rapidly as the motor speed increases. when the motor speed is going up, the torque decreases, right? So so that means when the initially the speed is low, you have a high torque, and then gradually speed increases and the torque decreases, right? So with that I finish the DC machines second presentation. um, so we will meet again with the third presentation of DC machines. Thank you.